Hello, welcome back. Hello, welcome back. So, it is time. It is time. We are officially doing mass balance. We're entering part two of chemical process analysis when we're actually doing mass balance. Now, for me, this was a very difficult concept. Well, not the concept's not too bad, which we're going to be going over today. It was more so the nuances of all the details in the calculation, and for me, that really got to me. So, the whole reason I started this playlist, the whole reason I started this channel was because I want to have a set of videos to help y'all, just like how I was struggling. I want to help y'all understand those difficult concepts and those difficult calculations and some tips and tricks. So we're going to be starting slow with mass balance, and I know I already have a video kind of talking about the general concept, but we're going to go a little bit more into it. We're officially starting part 2, which is chapter 4 in chemical process analysis. So this one might be a little bit slow paced, but we're going to start things to make sure we understand all the details and all these calculations. So this is going to be mass balance for chemical engineers, but super easy. So basically, in the previous video, I went over the most important equation in all of chemical engineering in undergrad, and you're just taking everything that's going into a system, subtracting everything that's going out, you're adding everything that's being generated, and you're subtracting everything that's being consumed. Okay, whether this is a cup of water, I might do a separate video just on this equation. It could be a cup of water, it could be a tank, it could be people in a country, it could be money in a factory, whatever, based on the conservation of mass. So on the conservation of mass, if you consider a mass balance, that's why it's called mass balance, you do accumulation, you add up everything that builds up within the system is equal to everything that's coming in, everything that's coming inside of the system, you subtract everything that's coming out, everything that's leaving the system, plus generation, so whatever's produced within the system, minus consumption, whatever's lost within the system. You might be thinking about, okay, well, mass cannot be created or destroyed, but when we see component mass balances, we do it by the individual atoms or something like that, and generation and consumption are due to reactions, and this could also be conservation of energy. So basically, every other class, as we'll see, uses this equation. So if you haven't seen this before, then make sure you memorize this. I don't advocate for memorizing, but if you're going to memorize something, it's going to be this equation. When in doubt, accumulation equals in minus out, plus generation minus consumption. Okay, makes sense? So we're building up everything that comes into the system. We're adding everything that comes in, subtract everything that comes out. You add everything that's being generated, you subtract everything that's being consumed. Okay? Any questions so far? Then leave it in the comments. Okay. So we can make some assumptions to make our calculations easier and more realistic when we don't have all these terms. So the first thing is, well, if there's no reaction, if there's just simply things going in due to transport, there's classes just on transport, there's classes just on the reactions, then we're going to assume that there's no generation or consumption for now. Later on, we're going to add it back in, and we'll see how that takes into consideration. Okay. So that's our first assumption. We're just going to say accumulation equals in minus out. When in doubt. That's because of no reaction. Okay, so steady state. If something is in steady state, that means the accumulation term is 0. Steady state means that there's no time derivative. There's no change with the system with respect to time. It doesn't mean that there's nothing coming in or out of the system. It just means that there's no buildup. I think I'm going to make a video on just steady state. But for now, kind of understand that if it's steady state, there's no buildup within the system, and you can imagine that there's no visible change per time. So the time derivative is 0. So we're going to say accumulation is 0 and equals in minus out. So now we have 0 equals in minus out. Okay, so we can try this with an example. So let's say we have some kind of system. Let's just say it's a tank with 500 kilograms of mass going into the system, and then it's being separated into 2 products. So the first product is in the top. It's going to be 200 kilograms per system, and the third product is in the bottoms. It's an unknown. Okay, so this one's a pretty simple mass balance, but we're going to do it from scratch, starting with the overall mass balance. So I want you to try it first and see if you can figure it out. Okay, I'm gonna give you a hint in 3 seconds if you're a little stuck. So 3, 2, 1. So we're just gonna simply write off the entire thing. Accumulation equals in minus out plus generation minus consumption. When in doubt, accumulation equals in minus out. We're gonna make the assumption that there's no reaction, so there's no generation or consumption, and we're gonna assume that it's steady state. So now we have 0 equals in minus out plus 0. So if 0 equals in minus out, then we can just simply write 0 equals everything that's coming in minus everything that's going out. So the thing that's coming in is 500, the thing that's coming out is 200 and M3. So there's two ways to solve this. We can either plug everything in, or what I like to do in this case, I like to write a general equation by not plugging it in, and I'm going to write everything coming in on one side and everything coming in on the other side. So m dot 1 is coming in on the left, and you're adding m dot 3 is coming on the right. Now you plug everything in, and you're going to get 500 equals 200 plus m dot 3, and doing some algebra, you can figure out the answer. Or you can plug it in first directly, knowing that m dot 1 is 100 and m dot 2 is 200. You can plug it in directly and can get that m dot 3 is 500 minus 200, same as here, and the answer is the same for both, 300 kilograms per second. Which makes sense, right? Because whenever you have something in, that's the mass balance. You have 500 on the left, 200 on top, and 300 on the bottom. Has to be equal conservation of mass. That's why it's called the mass balance. So now we see again, it's 500 and m dot 2, 300 kilograms per second. That's the mass balance. Okay, so let's talk about what happened here. If there's no generation or consumption, we say that the accumulation term, if you've taken calculus, you see that the accumulation term is dm over dt, the time rate of change of mass change with respect to time. However, and we add up everything coming in on the left, everything coming in, and you subtract everything coming out. So that's what the summation term means. You're adding up all these streams of fluid or mass, whatever's coming in on the left, going inside, and you're subtracting whatever's coming out. And now if you make the assumption that it's steady state, then dm dt goes to 0. So we have 0 equals summation m in minus summation m out. So these are all the streams coming in and all the streams coming out. And now we can say simply that in equals out. Everything coming in is equal to everything coming out. Mathematically speaking, we're writing all the summation terms that are coming in. We're summing up all the terms that are coming in on the inside, and we're setting it equal to all the terms that are leaving the system. Okay, so in equals out. And that's going to be pretty much our working equation for basically the entire rest of this class. But as we'll see, the actual equation won't be so simple, and when we get into more advanced classes, we'll see that we'll actually need more terms and we'll need some calculus. But for now, it's going to be all algebra, and might be a little bit tedious, as it was for me. In my experience, it was more tedious to do the algebra rather than to do the general mass balance with calculus. But that's my opinion. So basically, as a recap, we went over the entire when in doubt, accumulation equals in minus out plus generation minus consumption, and this is based on the conservation of mass. So remember, we're adding everything that's coming into the system, subtracting everything that's coming out. This is going to be produced, and this is consumed. And accumulation is the time rate of change. If it's a steady state, then it goes to 0. We did this example. We solved for M3. Remember, it's 500 equals 200 plus M3. So M3 is going to be simply, 300. And then we finally generalized the mass balance equation for systems at steady state without reactions as summation of everything coming in, setting equal to the summation of everything coming out. In equals out. That's going to be our main working equation. Okay, I think that's it for this video. Hopefully that makes sense. We're going to take it up a notch and do some more examples, and then go through the book and do a ton of problems. If you're getting a little frustrated, recommend you study it and go through the problems in the book, and hopefully it'll work out. All right.